We're supposed to talk about equilibrium. Okay. We'll be talking about chemical. All right. We also deal with things like happens in at every forward and backward reaction process. Okay. Okay, and also we'll also be dealing with the factors that affects chemical equilibrium. Okay, so these are the various things we deal with in this particular topic. So we'll also be talking about temperature as a factor that affects equilibrium. Talk about pressure. Talk about concentration. Okay, and how somehow these things are connected to each other. Would also be talking about some other side things and things to know. So this class is just going to be more like you already have learned this topic, so it's just going to be some things you need to know, okay, that would help you to be able to answer some questions. All right. I will be sharing my screen shortly.
Mom, not.
Oh, hello. Oh, I thought I didn't realize I was
Yeah,
muted. Can you see my screen? That's what I've been saying. Sorry about that. Can you hear me now? Hello? Winner and Melody, can you hear me now? Hmm.
yes, ma.
I Yeah, I didn't know I was muted. Okay. Okay, so I was saying that chemical equilibrium, we won't be talking so much about definitions and things like that, but chemical equilibrium have to do with a state in a chemical reaction where there is a forward process and there is a backward process, and the rate at which the rate of the forward reaction and that of the reverse or backward reaction is the same. Okay, so they move at this at exact same rates. That's what causes the equilibrium there. That's what equilibrium means. Equality, right? So the rates of forward and rate of backward are equality. That is to say, there is a balance between the reactant and the product. But why is it different from our normal reaction? Okay, this one is reversible. That means the way you can, for example, in this so for example we have, okay, that is to say the way you get um hi, okay, hydrogen iodide as a product, that is how you can this reaction can go back to forming hydrogen and iodine. So it's a reversible process. Okay, we can't say the same thing for a simple chemical reaction that just has only one arrow. Okay, so now I also mentioned that we'd also be talking about the various factors that affect chemical equilibrium. Okay, we have pressure, we have temperature, we have concentration. Okay, I'll be telling us the things where we should take note of, because if we want to be explaining into so much details, we won't have that much time to do that in this 1 hour class. Okay, so now one of the things we should take note of is that um we can detect the concentration, okay, especially when we are not calculating from the balanced reaction. Okay, so for example, if we have the equation I just used now, hydrogen plus iodine. If we have something like this is 1 mole of hydrogen, 1 mole of iodine to give us 2 mole of hydrogen iodide. Okay, so this is the simple process. Okay, so um we can determine our concentration from this, because we know that concentration is so much related to the coefficient of a reaction, right? So one thing we should note is that our number of mole is directly proportional to our pressure. Okay, that is to say, if number of mole is increasing, pressure is also increasing. Okay, so the higher the number of mole, the higher the pressure. The lower the number of mole, the lower the pressure. We can relate what our number of mole is by determining what the coefficient is. Okay, so for example, when we have reaction like this E here, when we have 2SO4 plus this. Okay, so we see that the coefficients are the reactants. We have 2 here, and we have one coefficient from the oxygen, right? This one, there's 2 here, and there's an invisible one here, and this is 2 here. So in the reactant we have 3, and in the product we just have 2, right? So these coefficients would stand as our n, which is our number of mole, and it is directly proportional to our pressure. So the side with the higher number of mole, okay, is going to tell us the side with an increased pressure. So that's one thing to note. Another thing to note is that uh, so if number of mole is directly proportional to pressure, concentration also is having direct proportionality to pressure. Okay, and then volume is having inverse proportionality to pressure. Okay, so now then how about catalyst in chemical equilibrium? Okay, even though catalyst is one factor, but it is not a factor. Um, okay. Now all these are factors, right? How are they They are factors that disturbs chemical equilibrium. So we already said chemical equilibrium have to do with balance, right? Between the forward and backward reaction process. Okay. So they must be happening at the same rate. So if there is any alteration to that balance, or anything is affecting that balance, if we are removing or adding anything, okay, it will be depending on if we are adding or removing pressure, we're adding or removing concentration or temperature. So there is the effect of that adding or removing is what we'll call equilibrium shift. Okay, so it can also help us to determine how much a product can be formed, where the reaction will be shifting to, if we're going to be getting more of this or more of that, if we'll be removing more of this or more of that. Okay, but then temperature is that's what we call equilibrium constant. Temperature is the only factor that affects, or rather that changes equilibrium constant. Temperature is the only factor that changes equilibrium constant K. Okay. So the value of equilibrium, so the number that we'll get when we are determining equilibrium constant, can be affected by just temperature. Okay. So to explain it, it's just like saying if we are dissolving sugar, for example, okay, in a hot water, and we are also dissolving sugar in a cold water. Okay, we are dissolving the same amount of sugar. So the fact that more sugar would dissolve in the hot water compared to that of the cold water is not dependent on the amount of sugar, because we are dissolving the same amount, but it's dependent on the temperature. Okay, so the constancy of equilibrium can be changed by just temperature as a factor, but equilibrium shifts is caused by temperature or pressure or concentration or even volume. Okay, so these are some things we should note. Now another thing we will go into details in different of about different aspects. Okay, another thing we should take note of is that, now how does each of these things affect? Now in terms of pressure, let us talk about pressure. For pressure, we know that pressure is something that in terms of in equilibrium, pressure should always be looked at in respect to gases. So if we are seeing an equilibrium equation, okay, we should focus on the gases, okay, and also we should also look at the number of moles. So it should be looked at in respect to gas particles only. How do you know they are gas particles? That G that you see by the side tells you that's a gas. In respect to gases alone, and determined by the number of molecules. Okay. So another so because of this, we should take note that equilibrium, please, I hope you people are jotting down. Equilibrium moves away from the side with more number of moles. More number of molecules. Uh-oh. Okay. That is when you are adding or increasing pressure. So, like I said, rather than going into details of what really happened in an actual system, I even had a video here to show to you people, but I probably would just send it directly on the group chat or something like that. So we don't spend time explaining, and we won't know how to deal with questions concerning it. Now, the reverse is the case for um, when pressure is being reduced. So we should know that equilibrium moves towards the side with more number of molecules when you remove or decrease or reduce pressure. So now let's see an example that would explain this for us, okay? So when we are being asked questions concerning how pressure would affect equilibrium shifts, if it's going to be shifting to the right or shifting to the left, we should first of all look at the number of mole, because remember I said at this beginning that number of mole is directly proportional to pressure. So the number of molecules tells us the side with more pressure, and that side with more pressure, when when in the side with more pressure, okay, equilibrium will move away from that side with more number of molecules if you are adding more pressure. But when you are adding when you're removing pressure, equilibrium will move towards the side with more number of molecule. Okay. So now, for example, we have, okay, now we have these questions. Can you all see my screen? All right. Now, in this particular question, is it which of the following is not affected by a change in pressure? This is a 2023 WAEC question. Okay, so we'll be starting with the first question, the first option. In the first option, like I said, when we are dealing with which side is the effect of pressure, we would first determine the side with the more number of mole. Okay. Now, if we look at this, the reactant in this A option, hydrogen is having one, is made of one molecule. This one molecule of hydrogen, because we are looking at the coefficients. There's only one coefficient here. For iodine, only one coefficient. They don't write it, right? Why for the HI, the hydrogen iodide, it is two coefficients. So in total, the reactant is having two coefficients and the product is having two coefficients, which means two number of mole and two number of mole. Now, the thing here is that there is no effect of pressure here. Why? Because the both the reactant and the product are having the same number of mole. Okay, so there would be no effect, because if we want to look at the effect of pressure, they have to be um difference in the number of moles so that we can be able to work for the side with a more number of mole. Okay, now in the option B, the reactant is N2 and 3 hydrogen forward and backward to give us 2 NH3. Okay, now the total number of mole in the reactant is 4 and that of the product is 2, because we have 1 from nitrogen and 3 from hydrogen, which gives us 4, and 2 from the ammonia, right? Okay, so that is to say it is the reactant side that has the more number of mole. That means pressure is going to affect this. Although the question is not asking us if it's going to the right or left. By the way, going to the right is the forward reaction. This top one is the forward reaction and it's called right, shifting to the right. And this bottom one, when it's going back, it means shifting to the left. So you don't call the top one right, left, or the, no matter which angle you are looking at your question paper from. Okay, so the top one is shifting to the right, the bottom one is shifting to the left. Now, for us to determine if this is shifting to the right or to the left, remember the what I told you to take note of earlier on, that pressure moves away from the side with more, I mean, equilibrium shifts away from the side with more number of mole, okay, when pressure is being added. Let me take it back for you people, for you all to see it. Equilibrium moves away from the side with more number of mole when you are adding or increasing pressure. Okay, so the side with one more number of mole is our reactant. Okay, and equilibrium will move away from it. That means it's going to be moving to our right. Okay, so this will be a shift to the right. Okay, the essence of all this is Le Chatelier's principle. This is where Le Chatelier comes in chemical equilibrium. The principle tells us the opposing character of gas particles that participate in chemical equilibrium. Okay, it says that if a chemical equilibrium is disturbed by changing the conditions, okay, the conditions can be pressure, temperature, volume, okay, the system will simultaneously shift its equilibrium position to counteract it, or to oppose. It will shift to oppose, okay, to oppose the change and reestablish a balance. So since we have more number of molecules in the reactant, it would imply that there are less in the product. And so equilibrium is shifting to the product side to oppose it. Okay, so the more we are um adding pressure, equilibrium will want to shift to cause a balance. All right, so this will be shifting to the right. That is to say, our option B is affected by pressure, and it is shifting forward. Now, how about option C? The number of mole in the reactant is 2, one from this first reactant and one from the second reactant, and that of the product is 1, right? And now the side with the more molecule is the reactant. And what do we say when pressure is being increased? If pressure is being increased, equilibrium will shift away from the side with more number of moles. So this is also going to give us forward reaction process. Okay, it's going to shift to the right. But what if pressure is being reduced or pressure is removed? Equilibrium will shift towards the side with more number of molecules. That is when this reaction can now shift to the left. So it's not always or every time going to be the right, okay? Especially when the reactant is more than the product. It's not always going to be moving towards the right. It can move towards the left, towards the side, can be the right or the left, towards the side with more number of mole. Okay, so whenever equilibrium is moving towards, usually it is when um there is reduced or removal of a particular condition, be it temperature or concentration or pressure. Okay, so when you are removing, it shifts towards that place you are removing from. Then when you are adding, it shifts away from that place you are considering. In this case now, we are considering the side with the more number of mole. And so when we had more pressure, it shifts away. That is why this one equilibrium is to the right. The same thing here to the right. Then how about the second one? This is 1 mole and this is 2 mole. When we add pressure, okay, it shifts away from this side that is having a higher number of mole. And if it is shifting away, it is going like when you are shifting away from something, you are opposing the thing. Okay, so for example, we have this A here. Shifting towards A will mean you are going towards A, right? Then shifting away from A will mean you are going away from A. So shifting away is what usually happens when you are adding a particular condition. You're adding pressure or you're adding temperature or you're adding concentration. Okay, so it will be shifting away from that side that we are considering, or that side that is being affected. Please, if you have understood so far, I want to see your response, or if you are confused. So if you notice, from the option B to E, they are all having difference in number of mole from reactant to product. Okay, can be 4 and 2, 3 and 4, like that. But you see the A, both the number of mole of reactant and that of product are the same. So there is no effect of pressure there. We have to, when we are dealing with effect of pressure, one, it must be a gas. Two, we must consider the side with more number of mole. And so if pressure is reduced, it goes towards. Um if pressure is added or increased, it goes away from that side with more number of mole. That's the simple rule to deal with equilibrium shift connecting with pressure rather. Now, how about temperature? When we're dealing with temperature, we're considering two aspects of temperature. So we have endothermic and exothermic reaction process. We'll talk about temperature. Okay. Now, I have a video, but we don't have that time to be watching this video. So in essence, endothermics just simply have to do with absorbing heat, and exothermic has to do with releasing heat. So some of the differences between exo and endothermic is that endothermic, okay, aside the fact that this one has to do with absorb and this one has to do with um release, okay. Endothermic also has to do with has a enthalpy change of it has a positive enthalpy change. What does that mean? Enthalpy change, okay, delta H is enthalpy, change is delta, is equal to product minus reactant. So when product is greater than reactant, you are going to get a positive number. For example, if your product is 3 and your reactant is 2, product minus reactant is going to be equals to 1, plus 1. Okay, so when product is greater than reactant, we have an endothermic process. While exothermic is negative, that is when product is less than reactant. So delta H is always product minus reactant. It's never reactant minus product. So we are removing the reactant from the product. So it's not going to be reversed if it is exothermic. Okay, so if our product is less than our reactant, let's say our product is 2 and our reactant is 5, okay, we are not going to now say the bigger number minus the smaller number. We're going to follow the formula P minus R, which is going to give us minus 3. So endothermic is usually negative, okay, and endothermic is heat that is released. So that is to say it is effective at the product side, not at the reactant. Okay, so exothermic is it follows what is formed. Okay, is a step that follows what is formed. While endothermic is being absorbed in the process of reaction before the product is formed. Okay, so heat is being absorbed, exothermic heat is being released. So this is an example, photosynthesis. You can see that heat is part of the reactant process, right? To give us this and this. Now, how about exothermic? You can see heat was formed in the product side. So, in terms of equilibrium, okay, equilibrium in terms of temperature, we should, just as in pressure, we're focusing on which side has the more number of mole. In this temperature, we will focus on which side the heat is. Is the heat in the reactant or in the product? If heat is in the reactant, it is an endothermic process. If heat is in the product, it's an exothermic process. What if you're not giving like this? If you see a positive enthalpy change, okay, for example, you see this whole thing. So rather than them writing heat, maybe there's no heat here. You just say CO2 plus water to give us glucose and oxygen. Then they now wrote something like plus 64. This tells you that this is an endothermic process, which would also mean that our heat is part of the reaction, like it's part of the reactant. But what if we put it was a negative 64? It will imply that our heat is part of the product, even without your equation writing it. Do you understand? Do you all understand? Hello.
No, ma.
Okay, so we are judging in terms. Okay, so what part do you not understand? I said endothermic has to do with absorbing heat. Okay, an example of endothermic process is, for example, you have an ice. Okay, now to maintain balance, the ice will melt because of the um, absorption of heat from the surrounding. Okay, so heat is being absorbed to lose the coldness of the ice. Then if it is exothermic, we have an example is hotness. Exothermic is those reactions that releases heat in the process. Okay, so if you're doing maybe a laboratory practical and at the end of the whole mixture or process you find hotness or warmness in your beaker, that's an exothermic process. Heat is being released, but endothermic, heat is not released, rather it is absorbed in the reaction process such that the product that will be formed won't see any release of heat. Now, Melody, I said that negative value of delta H implies exothermic reaction, while positive value implies endothermic reaction. Now, if the value is positive, that means it's endothermic. It means that the heat participated in the reactant side, not in the product, because it was absorbed during the reaction. That is, it was absorbed in the reactant with the reactant. Okay. Now, in exothermic, the heat is released, and so we will find it in the product side. So whenever we are talking about where equilibrium might shift towards, we would focus on where the heat is, if it is in the reactant or in the product side. Okay, how do we know where it is? Negative or positive sign? That is one way to know. All right, if it is negative, it is in product. If it's positive, it is in the reactant. Do you understand now, Melody?
Yes, ma.
Okay. Now, just as in pressure, we would also know where equilibrium will be shifting to here. Okay, once we have identified if it is endothermic or exothermic, equilibrium will shift away. Sorry. Equilibrium will shift away from the side where temperature has been added to, and it will shift towards the side where temperature has been added to. But let me write it down. Equilibrium will shift will shift away from the side heat is, okay, or from the side heat is added. Okay, and then it will shift towards the side towards the side, towards the side it is if you remove temperature. Okay, equilibrium will shift away from the side it is if temperature is increased. Please, if temp is increased. Okay, this is a better way to say it. If temperature is increased and it will move towards the side it is if you remove temperature. So it's somehow similar to that of pressure, but this time we are considering the side where the where our enthalpy is, or rather where our heat is, if it is absorbed or released. So let us see an example that explains this. Okay, now this question below. It says, consider the following reaction is increasing the temperature of the reaction would. Okay, are you seeing the question? What would increasing the temperature cause? Based on what we have noted now, we see that first off, what are we going to look at? This delta H, this information is not giving us here for nothing, right? This tells us that our heat is where? Is it in the reactant or product side? Melody winner, anyone can answer. Or golden. This delta H being minus 92 kilojoule, it tells us what? Does it tell us endothermic or exothermic?
Exothermic.
Very good. And so since it tells us exothermic, what does that imply? That our heat is going to be part of the reactant or part of the product? You know, if something is exothermic, it means heat is released. So what side is releasing favoring? Where would release of heat go to? Just as we had up here, I told you heat will participate in the process. If it is endothermic, that's why heat is written here, positive. If it is exothermic, heat is at this other side. So now in this our question, it means that heat is where? Is heat part of the reactant or is part of the product?
Product.
Very good, product. That is to say, we can somehow now write this reaction to be like this. 3 hydrogen gas forward and backward to give us 2 NH3 gas plus heat. Are you seeing it? So we can write it like this. This tells us that it is an exothermic process. Now we want to know what increasing temperature would cause. Remember we said based on this statement that we have to take note of, we said that if we increase the temperature, okay, equilibrium will shift away from the side where it is, right? Equilibrium will shift away from the side where heat is. I'm going to answer this question with us. The next one, you people will answer it. Or in fact, you people should we answer this particular one. Equilibrium will shift away from the side where heat is. So tell me, what is the shift here? Is the shift to the right or to the left?
Left.
Very good. It's to the left. So equilibrium will shift towards the left because the heat is here. So it's going to go away from it, right? So that is to say our A is not the answer because A said equilibrium will shift to the right. Now the second says that uh, increasing temperature will increase the yield of ammonia. Okay, we can see that heat is being heat is being released here. Now let us consider our C and D as well. Our C says decreasing it will decrease the amount of hydrogen. Now um increasing temperature, since our equilibrium is moving towards the left, okay, hydrogen, since this is an exothermic process, okay, hydrogen is not going to be decreased. Now we have D, it will decrease the yield of ammonia. Okay, since our equilibrium is shifting to the left, right, is going to imply that ammonia, the yield of ammonia is going to be decreased because this left is favoring the reactant and not the product. So when we are moving towards the left, it's more like more of reactant is formed, okay, and less of product is favored. And in the right, more of product is favored and less of reactant is favored. Okay, so since it is going towards the left, what is favored here is more of reactant and less of product. Okay, now B says it will increase the yield of ammonia. That means more of product increases more of ammonia. Ammonia is the product, right? And you see that that's not true in backward reaction, in left reaction, because we see that it is reducing product and increasing reactant. So options that is saying increasing products is not true for left reaction. Okay, now C says decrease the amount of hydrogen. Let's in left reaction, react, it means more of reactant, not less of reactant. Hydrogen is a reactant. Okay, so it's not going to decrease but increase the amount of reactant, which is hydrogen. It can be hydrogen or nitrogen. Now D says it decreased the yield of ammonia, which is true because in the backward reaction we have less of product. Are you people seeing it? With more practice, this topic is actually like when you know the tricks, the ways to follow, is actually plain and easy and straightforward. Do you understand what I just explained? So this is another thing you should note. This thing I just wrote down. Going to the left side, okay, it implies what? It implies less product and more reactant. So in essence, this negative 92 is what is telling us that it is with products, and which will tell us that if we're increasing temperature, it will go away from that product side. And if it goes away from product side, means it's going to the left. And so if it is going to the left, by consequence, it means that we should be expecting less product formed and more reactants used. Okay, B is saying that it's more reactants formed, which is not accurate. C is saying um less reactants used, which is not accurate. Are you saying it? Then for the forward reaction, assuming we're dealing with forward reaction, it will mean what? More products formed and less reactants used. Okay, so this is just another thing to take notes alongside your the initial things I told you to jot down. Okay. Please, if you have any question, you can ask. But let's just handle this. Okay, if you have any question, please do ask. Then in the next class, we could continue more previous questions. I think we should continue this topic. Who was the person that said we should do chemical equilibrium? Is it Golden? We didn't even talk about equation like equilibrium constant, how to write the formula. Golden, were you the ones that said we should do this topic? Golden.
Yes, ma'am.
Okay. Now, so far, do you understand the topic? Do you understand the lesson today?
Yes, ma'am.
Okay. The rest of you, please, if you have questions, you can ask. Okay, so I'm assuming there is no question. Yeah, no questions. Okay, if there are no questions, Rina and Melody, in fact, any one of you, this question particularly, this one that is on the screen now, please, I want an answer. What's the answer? Which of the following statements is correct? Yeah, someone should answer us.
D.
D, very good. It is absorbed because it is positive, so it's endothermic. Good. So, what do you people like us to learn in the next class? Should we continue with chemical equilibrium or we should talk about another topic? Since none of you have any question. Yeah, someone should say something. Hello? Should we continue with this topic or we should talk about something else in the next class?
Ma, we should do stoichiometry.
Stoichiometry, was that not what we did in the first class?
Yes, like a deeper note on it.
Deeper notes. So that is to say, you people are comfortable. You're not comfortable with chemical equilibrium. We should not continue this topic.
No.
Winner and Golden, you understood that because we've not touched some parts. That's why I'm asking. We didn't talk about concentration. We didn't talk about varieties of aspects that
Okay,
you
ma,
might be asked questions.
when we're through with this topic, then we can do that one.
Okay, because I'm asking, maybe probably you already have good knowledge about it from school. So that's why I have to ask. So that in case you do, maybe there will be no need for us to talk so much about it. But I think we should continue this one. Then in the next class we'll talk about stoichiometry. Your practical exam is next tomorrow, right?
Yes, ma.
Hmm. Okay. Study. You can go back to the videos I sent. Study enough. Make your writings clear. Um, some of all these things, little errors cost you marks. So be careful when you are writing down, and also study. At the end of the day, you already have an idea of the kind of things you'll be doing because you know the reagents you are using already. So you know that you're carrying out the neutralization process, titration, and you also know that you are um, having qualitative analysis. Okay. All right, that will be all. Since you all have no questions, I hope you learned something today. Um, I believe you did. All right. Bye bye.